All right, hello there. So today we're going to do notes for section 12.1 and 12.2. And so just to say at the beginning here, I've put the blank copy, a blank PDF of these on Schoology, and you're welcome to print them out and write on there. If you don't want to print them out, that's fine. You could just pretty much kind of copy the things that I write or the things that you feel like that you want to write down or have for the future. Just pause and write them down. I'm going to try to go kind of quick here, and every once in a while there might be a little question that gets put in there that you have to answer before you move on in Edpuzzle. And one more thing to note. So notice these section numbers up here. These section numbers, I've changed them to match what the PDF of the book is on Schoology. So that PDF, for some reason, it says 6th edition, and the books that we have in class are also 6th edition, but for some reason, they're like one chapter off of each other. So later, when I post the answers to these two sections, the homework or classwork answers, it's going to say chapter 13, whereas in the book online, it's going to say chapter 12. So just so you know that, and the problems are the same. I've made sure that they're the same problems. I don't know why. Anyway, here we go. So like we talked about in class, just some examples of different ways you can see 3D space. So when you see three-dimensional, that's R3 right there, like the real number system cubed. And so just pay attention to how your axes are. Like here, you have your X there, your Y, and your Z, so it's kind of framed that way. And when I draw these myself, I frequently do kind of like a V shape like that, and that is my X and my Y axis, and then I have my Z axis going up there. So if you want to draw this by hand, and then if you want to show going negative, you kind of put like little dotted pieces going back and this way. So for example, let's say you wanted to graph the point, like 2, -5, 4, something like that. And so I'd go 2 this way, 5 back this way, and then 4, so up 1, 2, 3, 4. So let me make sure. 2, -5, 4. Yep. And so maybe you'd graph it like right about here. It's not going to look that good. It's just going to, be the best you can do because you are graphing something that's in 3D but on a 2D piece of paper. So anyway, we talked about in class. So here's like a picture of a plane right here. This is the equation y = 5. Remember when you would have in the old X and Y axis, you would have a line. If you had y = 5, you would be crossing the Y axis at the number 5. Well, you see this plane is crossing the Y axis at 5, but it's a plane now because it has to be in 3D. All right, so when you talk about distance, back in geometry or algebra 1, if you remember, this used to be your distance formula, but now you have a third part, that Z value added on there, or that part. And so if I want a distance between 2 points, I basically use that, and I have these points graphed here. Point A is right here, and here's point B, and I want to know the distance between these two things. All right, so my distance is going to be the square root, and basically all you're doing is doing the difference between these two pieces. It doesn't matter which one's first because you're squaring it. So the difference between 2 and -3 is a space of 5. I'm going to square it. And then the distance between 5 and 4 is 1, so I'm going to square that. And distance between -4 and 0 is 4, so I'm going to square that. So just don't worry about the negatives. All right, so I got 25 plus 1 plus 16, so I have the square root of 42. That's my distance. Now, if you were in physics and somebody asked you to think of a vector going between these two spots, I want you to write in Edpuzzle, if you had a vector starting at A and going to B, this vector right here, what would that be called if you figured out the length of that vector, the distance between the two? And I'll give you a hint, it starts with an M. All right, so hopefully you typed in there the word magnitude. All right, and so magnitude, if you had that vector AB, you'd denote it like that, and somebody was doing the magnitude, you'd put these straight lines around it. So the magnitude of a vector is when you put those bars around it. They look like absolute value bars, but there's no such thing as the absolute value of a vector, so they're magnitude bars. And every once in a while, you might see double bars, but we use singles. All right, so equation of a sphere. So again, from geometry class or yeah, probably geometry or pre-calculus, you should recognize this piece and this piece. If you had that, that would be a circle in 2 dimensions. Well, now we have 3 dimensions, so we're putting on this portion right there. So if you were going to be in the center, this h, k, and l would be 0, so your equation would turn into x squared plus y squared plus z squared equals, and a number squared, that radius. So start to recognize that pattern right there. So if you had something like, x squared plus y squared plus z squared, so if you had all your variables squared and they're all positive, and then you had equal to a number like, let's say 16, you'd be like, oh, I have a sphere with a radius of 4. Okay, so start to recognize those equations just like you would if you're trying to recognize a line or a circle. All right, so sometimes your equation might be all messed up, and so this one right here, we got x squared and we got 4x, so I'm going to pair those together. So I got x squared plus 4x, leave a little space. Remember, I have to complete the square. I have y squared minus 6y, leave a little space. Then I have z squared plus 2z. Leave a little space, equals, and move that 6 over, so negative 6. So I hope that negative 6, I hope that turns positive, because otherwise we're in trouble. So remember, to complete the square, I take half of the middle term. So half of this 4 is 2, 2 squared is 4. Half of 6 is 3, 3 squared is 9, so I add 9. And half of 2 over here is 1, and I square it, I get 1. Well, I want to make sure that those values right here, this one, and this one, I also have to add those to the other side. So add 4, add 9, and add 1 to be fair, to keep my equation balanced. All right, so what I end up with, if I factor as I go, x plus 2 squared plus y minus 3 squared plus z plus 1 squared equals, and over there, let's see, that totals up to 14 minus 6, so 8. So if you ask me now, I would say I have a sphere with a center of negative 2, 3, and negative 1, and the radius is the square root of 8. There we go. All right. So, basically what you have, if you want to kind of draw it out or think of it like that, x, y, z, and let's see, negative 2, 3, and negative 1, so negative 2, 3, and negative 1, so maybe that's about like right here, and my sphere, square root of 8, so, just trying to estimate here, so I have a sphere, and there's my center right there, so I know that looks ugly, but again, you try to draw it. All right. So you have to be able also to understand situations and what's limiting you. So these next few examples are just talking about shape that gets created when you limit yourself by certain equations or inequalities given to you. So this first one, so if you were, don't cross this off, but if you were to look at this and this was going to be an equation right here, you'd be like, oh, that's a sphere with a radius of 2. And if the 1 was still there, you'd be like, oh, that's a sphere with radius 1. So by putting those inequality symbols there, that's telling you I want the sphere, but I want the radiuses to stay between 2 and 1. So I want the space in between those two spheres. And so think about like a basketball with like a really thick like material, or think of like if you ever like a cantaloupe, like a cantaloupe has like it has like the fleshy part of the part that you eat and with the skin, and then the insides are seeds. So if you look at this picture right here, it's almost like you scooped out the middle right there, right? And so whatever you want to think of. Anyway, so that would be, if you just had this piece right here, you would say to yourself, well, I have a sphere, and what's happening is there's a sphere, and it's only the space between a sphere of 1 and a sphere of radius 2. So it's like the space in between those two things. All right, so this is a much better picture right here. So I'm gonna tell you to explain this in words as well, because obviously we can't all draw pictures like the book does. Well, I also have this part right here. So normally if I had just this, I would say it's the whole sphere, but then somebody came along and said, hey, only use z values that are less than or equal to 0. And so that means that my sphere gets chopped in half, and I'm only using the bottom portion of it for z values less than or equal to 0. So this is exactly the picture that I end up with. Okay, so we also want to describe it. So what we want to do, since I can't draw pictures that well, I want to say it's the space between spheres with radius or radii 1 and 2 at the center. That doesn't make sense. Not at the center, just the center is the origin. How about with center at the origin? All right. And we only want z values less than or equal to 0, so and the bottom half. Okay, so just some way to describe it, so in case your picture kind of stinks, then you have the words to describe it. All right, so the next one says, let's think about this equation y equals z in 3D. So I want you to always try to think back to, what does that mean to be me if it was in 2 dimensions? I would only have x and y. So if I was graphing the line like y equals x, let's say, I would graph this line right between y and x. So it's going to be the same idea over here. It's going to be something linear looking between y and z, right between these two guys right here. So it's going to follow equal distance between those two. But remember, in 3D, your basic shape is going to be a plane. So it's actually a plane that's traveling, and I have a better picture on the next page, a plane that's like traveling diagonal between y and z. So I'd want to say this. It's a plane equidistant from the y and z axes. Or you could also mention it's 45 degrees because that's what the angle would be at. So if you look at over here, I tried to exemplify this and show you that in these two pictures here. So you can kind of see that angle right there, 45 degrees and so forth. All right, so the last one here says what region in R3 is represented by this inequality. So imagine you were in like 2 dimensions and you had x squared plus y squared equals 16. You'd be like, okay, well that's a circle with radius 4. Well, that's the same thing, you know, it's involving the x and the y axis. This is involving the y and the z axis. So again, involving these two things. So it's kind of like a circular shape with radius 4 right there. But look, nobody mentions the x value. So the circle that I just drew has an x value of 0. Well, it's also a circle with an x value of 1, and a circle with an x value of 2, and 3, and 4. And in fact, it's a circle with that radius, but it's also everything underneath it all the way down to 0. So that circle that I'm drawing is actually like kind of shaded in and solid. So this goes all the way along the x-axis and it's all filled in. So what you end up getting is more of a cylinder. So I would say this is a solid cylinder with radius equal to 4 along the x-axis. Okay, so a good picture of that, this green one right here. And so basically the missing letter is the axis that you're following along or the direction that you're going, because nobody told you what to do with that, so you can be anything. But you're limited on the y and the z plane to just that equation. All right, so now we're on section 12.2. So we have talking about vectors a little bit. This should be all review. A vector is a directed line segment. All right. Equivalent vectors have identical direction and length. And remember, when you're talking about the length of a vector, that's its magnitude. Okay. All right. So the component form of a vector. When you have a vector that starts at one place and ends at another, so in this one right here, we have this vector starting here, that's 2, 5, negative 4, and it's ending up there. And so we're calling that vector W. Remember, you can do the component form of a vector. You have to put these little bracket arrow brackets on the side, and you basically just want to do the X, the Y, and the Z direction. And so what that does is it tells you how to get from the beginning to the end going in certain directions if you were starting at the origin. So you take the terminal point and subtract the initial point. So like negative 3 minus 2 would be negative 5. 4 minus 5 would be negative 1, and 0 minus negative 4 would be 4. So that means that you can take that vector and you can put it anywhere. So if you want to take this vector right here and you wanted to replace it somewhere else, like for instance, put it like starting right here, and then you could go negative 5, negative 1, 4, and do that same direction and like repeat yourself. Okay, and so that's how you do it. All right, the length or the magnitude of a vector. So, the length or the magnitude of a vector has to do with the distance formula. The distance formula is you're doing the distance between 2 points is basically what you're doing. And so when you have something in component form, this right here, remember, is already the difference between these two things. This right here is a difference between these two. And then this piece right here is a difference between the z values. So really what I've done is I've done the x2 minus x1, y2 minus y1, and z2 minus z1. I just haven't squared them and added them up. So when something's in component form, it's just very simple to go ahead and square each part, add them up, and do the square root. So in this one, let's see, -5, -1, 4. If I was doing the magnitude of that vector right there, I would say the square root of 25 plus 1 plus 16. So the magnitude of that vector, the length of it, is the square root of 42. Okay, and so the length or magnitude of a vector, to do that, you do basically the square root, and you got your x squared plus y squared plus z squared. So these are like the component forms. Just kind of like an easy definition there. Okay. All right, so find the component form and the magnitude of this vector AB given here. So I'm going to leave that for you to tell me in the ed puzzle. I want you to find me the component form, and you can just put these little brackets and put the 3 numbers, okay, and then also find me the magnitude. So you can write like magnitude equals, and then I understand that if it's a weird square root, you can just write, square root of, and then put the number, okay? All right. So hopefully up there on that answer right there that you got that the component form was -5, 12, and -1, and the magnitude was the square root of 170. Okay. All right. So the parallel vectors. So parallel vectors, they don't have to have the same length, but they have to have the same direction. Obviously. All right. So when vectors have the same direction, what happens is that they are scalar multiples of one another. And I can do this a little bit easier with something with 2 dimensions. So for instance, let's say you had a vector of like 1, 2. So that means that you have a vector that is going 1 in the x direction, 2 in the y direction, so it's like that. So then if you came along and said, hey, let's do a vector of 2, 4. All right, so if I went 2, 4, I'd go out 2 and up 4, be up here, would be the same direction. It'd be the same parallel, because basically you kept like the slope ratio the same. So it's a little easier to see in 2D, but what you want to remember, they are scalar multiples of each other. So they're different lengths, but the same direction. All right, so your basic vector operations here. So like, let's say you had a vector that was like this, and we'll call that vector v. Well, if somebody came along and said, I want 2v, be like, okay, well, let me keep the same direction, but I'll double the length of that. Well, let's say I want -v. So let me keep the same length, but go the opposite direction. Let's say I want 1.5v. So I keep the same vector and then do half of it again. Okay, so there's just different operations, and that's like kind of pictorially what you're doing here. So over here, when something's in component form, it's really easy to manipulate them. So if you have 2v, so that means I'm going to do 2 times -2 and 1. Plus w, so plus 3 and 2. So that means I would get -4 plus 3 for my x value, so it'd be -1. And I get 2 plus 2 for my y value, so it'd be 4. So basically I'm just distributing and then like combining the x's and combining the y's to get my answer. Well, if I wanted to see that in a picture, I would say to myself, well, double v. So v is -2, 1, so I'm going to go -4, 2. So I would take that, and I would start here and go -4 and up 2. There would be my 2v. All right, and then I would tack on to that. At the end of that, I would add on 3, 2. So from the end here, I'd go to the right 3 and up 2. All right, and then watch this. This is my resultant. So the answer right there is my resultant. Oh, it looks ugly. Sorry. All right, and look at that resultant. That resultant starts here, goes left 1 and up 4. Exactly what you said it should do. All right, so over here, if I had w minus v, so I would take 3, 2. and I would subtract v, which is negative 2, 1. Now remember, subtraction is like adding the opposite. So if I was going to do this, I would take 3, 2 over 3 and up 2. There's my vector w. I would add the opposite, so add the 2, negative 1. So onto the end of this, I would go to the right 2 and down 1. Right? And look at that resultant right there. It is over 5. Oops, I forgot to do the answer. This is 5 and 1, right? That resultant is over 5 and up 1. So the picture kind of checks out. So the resultant and displacement vector, those are the two words that kind of go with that. All right. So next thing, and we're almost done here, is about unit vectors. So I'm going to stop the video and ask, what do you think a unit vector is? All right, so a unit vector, it's a vector that has a magnitude of 1, okay? And so what you want to do to get something that has a magnitude of 1, you want to get rid of its magnitude. You want to keep the same direction. So you want a parallel vector to the original vector, but you want the magnitude to be 1. So this is what you do. So you take your own vector and you divide it by its own magnitude, okay? So this will be a unit vector in the same direction as vector u, okay? All right, so we're going to find a unit vector in this direction. So I need the magnitude, so that would be the square root of 16 plus 1 plus 4, so square root of 21. So it's going to be really ugly, but the unit vector is going to be 4 over radical 21, comma, negative 1 over radical 21, comma, 2 over radical 21. So there we go. And sometimes it works out not so ugly, but if I go ahead and do the magnitude of this thing, watch what happens. If you square this part, you get 16 over 21. If you square this part, you get 1 over 21. If you square this part, you get 4 over 21. And square root that. So that adds up to 21 over 21. And what's the square root of 21 over 21? Hey, guess what? 1. All right, so you have what are called the standard unit vectors. This is another way of writing something instead of in component form. So a standard unit vector I is the vector 1, 0, 0. It goes 1 unit in the x direction. J is 0, 1, 0, and K is 0, 0, 1. So if you had a vector like my vector u right here, I could also write u like this. I could write 4i minus j plus 2k, and it would be telling you the same thing as the component form. All right, so our last little bit right here. Oh, so I just did that. So why don't you write that for me in your ed puzzle? I'll make one more little question right here. Write that right here. I want the standard form of this vector right here, which is in component form right now. All right, so vector w, this little arrow should probably be there. Vector w is 3i plus 4j minus 6k. All right, and so you can do the same operations. So if I had to do this, 2u, so I had 2 times 4i minus 2j plus k minus 3v, so this is supposed to be a v right here, and I have negative I plus 3j minus 2k, and so basically you just combine like terms. I have 8i plus 3i coming to me, so I have 11i. I have negative 4j minus 9j, sorry, negative 4, negative 9, so negative 13j coming to me. And let's see, up front I have 2k, and then I'm going to have plus 6k, so plus 8k. So there would be my answer right there. And let me make sure I didn't make any mistakes right there. Yep, all good. All right, so this right here is not free to do right now, but later we're going to work on that in class a little bit and make sure everybody got the video. And